Hello everyone, and welcome back. Over the last several lectures we have been looking at torques and how that affects the motion of something, how it affects its rotational motion, how we can relate translational and rotational motion. We're going to do that in a slightly different way now. What we're going to do is we're going to make a couple assumptions. We're going to assume that the system that we're looking at has a zero velocity. If the velocity is zero, the acceleration is zero. Not just instantaneously, but I mean like permanently zero. If the velocity is constantly zero, the acceleration is zero. And if the acceleration is zero, the net force acting on the object has to be zero. Likewise, we're going to assume that the object is not rotating, so that omega is equal to zero. If omega is equal to zero, alpha is equal to zero. And if alpha is equal to zero, the net torque acting on the object is equal to zero. So we're going to assume these two conditions. The net force acting on our object is equal to zero, and that would be a vector equation. So we're going to break it down into two parts. The net force in the x direction is zero, the net force in the y direction is zero. We could also say the net force in the z direction is also zero, but typically we'll limit ourselves to two-dimensional problems. Likewise, the net torque is equal to zero. And then what we're going to do is, given these conditions, we can solve a whole bunch of different problems. But this type of problem is called a static problem, or a system that is in static equilibrium or mechanical equilibrium. This brings us to section 12, which is entitled Static Equilibrium of a Rigid Body. A rigid body basically means a solid body. We're not going to assume that our system is a mass of separate points that are free to move separately. So we're going to assume we have a single solid object that is in static equilibrium. In other words, the net torque the net force acting on it is zero, and the net torque acting on it is zero. I know that we have skipped over section 11. That is on gravitation, and we'll be doing that right after we finish section 12. Okay, let's start taking a look at some problems. Let's imagine that we have a 10-meter long massless plank or board. We'll start off massless just for simplicity now, and we'll talk later on about how we would solve this problem if the plank actually did have mass. So let's imagine this plank, this 10-meter long massless plank, is sitting on two scales. So there's one scale over here at one end, the other scale over here at another end, and that's what's supporting the plank. And then let's say 8 meters from this end, there's a weight sitting on the plank with a weight of 50 newtons. Let's see if we can figure out what the readings on these scales would be. In other words, what would the force be that this scale exerts on the plank at the left end? We'll call this F sub L for the force on the left. And what force would this scale exert on this plank, this end of the plank? Over on this side, we'll call this F sub R. Okay, great. So the object in question is the plank. What do we know? We know the net force in the x direction has to be zero. Well, if we have a coordinate system x and y like this, okay. There are no forces acting in the x direction, so we don't have to worry about that. What do we know? Also, we know the net force acting in the y direction has to be zero. Let's define upward as positive. So what forces do we have in the y direction? Well, FL is in the positive y direction. FR is in the positive y direction. And then the 50 newtons is in the negative y direction. So minus 50 newtons. All of that is the total net force in the y direction, and we know that must equal zero. So bringing the 50 over there, we know that the sum of FL plus FR must be 50 newtons. But if that's all we knew at this point, we wouldn't be able to finish it. All we could say is that this force plus this force had to equal 50 newtons. We've already used the force conditions, Fx equals 0, Fy equals 0. What else can we do? Well, now we see why it's important to have that other condition, the torque condition. We know the net torque acting on the plank has to be zero. Well, to define torques, we need to choose an origin. So where do we want to put the origin? Well, let's just put it over here, just for now. We'll put it over at this end. So here's our origin. So what do we know? We know the net torque must be equal to 0. Let's add them up for each force. What's the torque due to F sub L? I want you to think about that for a second. It's 0. Why is it 0? Because FL acts at the origin. So what is R? Let's remember. What is torque equal? The magnitude of the torque is equal to RF sine theta, where F is the force, R is the distance from the origin to the point where the force is applied. If the force is applied at the origin, then R is 0, so the torque is 0. So FL exerts no torque on the plank. Okay? And then we've got a torque from the 50 Newton weight and a torque from the right force. Are they going to be the same sign? Remember, torques in the counterclockwise direction are considered positive. That we'll say those are positive. Torques in the clockwise direction are negative. Now the plank is not moving. How do we know what direction the torque is? Well, just think about it. In what direction is the force tending to rotate the object? Even if it's not rotating, which way is it trying to rotate the object, so to speak? So FR is pushing this way, trying to rotate the object this way. If I had a meter stick, think about this. If the meter stick could actually rotate and this force were to move the meter stick, it would move this meter stick in a counterclockwise direction. So FR is exerting a positive torque. So torque from FR will be RF sine theta. What is little r for FR? Well, FR is being exerted at a distance of 10 meters from the origin. So it will be 10 meters times the force, which is FR, times sine of theta. Now what's theta? Remember, theta is defined as the angle between R and F. F is the force. What's R? R is the vector from the origin to the point where the force is applied. In other words, here's the origin, here's the point where the force is applied. R for FR is this vector right here. That's R for FR. And what's the angle between them? Well, put them tail to tail. So here's FR, here is R, tail to tail. What's the angle between them? 90 degrees. So we have sine 90 degrees. Okay? Then the torque due to the 50 Newton weight. We know it's going to be in the negative direction. Why doesn't the negative sign come in there to begin with? Well, remember, the signs, the negative or positive, come about when we actually look at the vector form of tau and we were to use the right-hand rule. So if we were to actually apply the right-hand rule, we rotate our fingers from R to F. So for this one, R, F, rotate our fingers R to F, and that's in the positive, out of the board direction, positive. So that's positive. So rotating from R to F, here's R, here's F. For this one, that would be in the negative direction. So that's where the negative sign comes from. In other words, we know it's a negative torque. It's a clockwise torque. So minus R. What is R for the 50 Newton weight? What's the distance from the origin to the point where it's applied? 8 meters. So 8 meters times the force, 50 newtons, times sine of theta. Again, what's theta? Think about it. Again, it's 90 degrees, so sine of 90. And that equals the net torque, and we know the net torque must equal 0. Well, sine of 90 we know is 1, so we can take that out from both of these. And what do we have? We have 10 meters times FR minus 8 times 50. 8 times 50 is 400. Bring that over to the other side. And what do we have? We have FR equals 400 Newton meters divided by 10 meters, or FR equals 40 newtons. FR is 40 newtons. Now, if FR plus FL is 50 newtons, we know FL is 10 newtons. There we go. Very, very good. Let's think about this just for a second, though. We solved this by choosing the origin over here and assumed those torques then summed to 0. What if we had chosen the origin somewhere else? What if we had chosen the origin, for example, at the location of the 50 Newton mass? Well, if we had done that, we would have, well, let's just use these forces and see if we still get a 0 net torque. So Fr times this distance, well, that would be 2 meters. So Fr times 2 is 80 Newton meters. While for Fl, this would now be 8 meters times 10 newtons, which is 80 Newton meters. So again, positive from Fr, negative from Fl. Again, we get the net torque equal to 0 if we choose the origin here. What about if we chose the origin over here? Well, in that case, the 50 Newton force would be a positive torque, and R, in this case, would be 2 meters. 2 times 50 is 100 Newton meters. Now, what about FL? FL is 10 times 10 meters, 100 Newton meters. Again, we get the net torque is equal to 0. This is a very, very interesting result. Let's just think about this. If we have a stationary object and we choose our origin over here and we solve for 0 torque, what we're saying is that the net torque with this as our origin is 0 because the object is not rotating about this point. There's no rotation about it, so the net torque about here is 0. But if the object is stationary, then it's not rotating about this point either. So the net torque about this point must be 0. But it's not rotating about this point either, so the net torque about this point has to be 0. What we can keep in mind is that if the object is not moving, then it doesn't matter where we choose the origin. We can choose it anywhere we want. The net torque about that origin, or calculated using that origin, the net torque has to be 0. Well, this is a very, very powerful tool for us to use. What that means is that we choose the point of our origin to help us solve the problem. I chose it here, which removed one of the torques from our torque equation. The torque due to FL was 0, so that FL didn't even appear in our torque equation. By choosing our origin where one or more of the forces act, you can remove those torques from the torque equation and typically, hopefully, make it easier to solve. So that's a great thing to keep in mind, and we're going to use that for all of our other problems. Okay, let's take a look at something else.